All right, in this video I'm going to talk a little bit about how potential energy depends on separation and not location. So what we're going to do is we're going to imagine an object that's sitting here at some initial location. And over some amount of time, through an interaction with another object, which is sitting over here, we'll call this one mass 1 and call this one mass 2. These two objects change their location. They displace some amount. And so after some amount of time, maybe this object, which apparently I've drawn at a different size, displaces through a displacement delta R1. And this one displaces through delta R2. Okay, and the idea here is that we're trying to keep track of the separation between these two to calculate what the work that's done. So we're going to pay attention to the change in potential energy, which, as we learned, was the negative of the internal work. And so we're going to calculate the internal work for the system consisting of these two particles over their displacements. And so that internal work is given by the force on object 1 times its displacement plus the force on object 2 times its displacement. And through Newton's third law, we know that the force that object 1 exerts on 2, namely F2, is the same size but in the opposite direction that the force on object 2 exerts on 1, namely F1. So in that case, we can write down F1 is minus F2. We can put this information into our work calculation, and we can find that the work is actually F2 dotted into the difference in these two displacements, R2 minus delta R1. Now we can expand that out a little bit and try to understand what happens when we consider those actual displacements. So we will do a small calculation here. We'll allow R2 to move from R2 initial to R2 final. So we'll take the difference between R2 final and R2 initial. That's this displacement, delta R2. And from that, we will subtract off the displacement of mass 1, which gives you sort of the same kind of result, but for R1 final minus R1 initial. Now I'm going to move these around a little bit. I'm going to take all of the finals and move them over to the left side, and take all the initials and move them over to the right side. And we will calculate then the dot product of R2 final. There's a minus sign to be careful with here. R1 minus R1 final. And from that, we will subtract off. There's a minus sign here for R2. R2 initial minus R1 initial. And so now we have everything that depends on the final positions on the left subtracted from everything that depends on the initial positions on the right. Now, if you're paying attention at home, what you find is that this separation vector, this difference between R2 final and R1 final, is precisely the vector which points from mass 1 to mass 2 over this sort of interval here. So this vector that we have here, this difference vector, is actually the separation vector, which points from mass 1 to mass 2. And similarly, the difference between R2 initial and R1 initial is the separation vector which points between their initial locations. So what we're subtracting off here is the initial location. And so the internal work depends on the difference between these separation vectors. So in fact, what we have is something which depends on a quantity that we'll define as delta R, which is how the separation vectors going from R initial to R final, how those vectors change with time. So this right here tells us that the internal work depends on how the separation changes, not the actual locations. And up to a minus sign, that's how the change in potential energy can be thought of.